So we've been talking about exponential functions, but we haven't gone into how to solve equations with exponents that have different bases. So one thing that we can use to solve them is we can use their inverse, and the inverse of an exponential function is called a logarithm. So a logarithmic function is going to be written as y equals log base a of x. So now, one thing you can do is you can rewrite a logarithm as an exponential function. The way that you would write it as an exponential function would be x equals a to the y power. So you'll notice that the base a of the logarithm is also the base of the exponent. This y right here, that actually is my exponent, and actually the answer to the logarithmic equation is going to be your exponent. So keep that in mind, that whatever you're finding when you're taking a logarithm, you're looking for your exponent. The x in there doesn't really have any special name. I sometimes call it the answer. I don't really care what you call it, whatever works for you. But just remember that the base of the exponent and the base of the logarithm are equivalent, and the answer that you get when you take a logarithm of something is equivalent to the exponent in an exponential function. So the first type of example we're going to do is one where you're going to rewrite your logarithmic function as an exponential function. So my first one, I have log base 3 of 81 is equal to 4. Remember that the 3 is the base, the 4 is the exponent, and then I just have that equals 81. You can kind of tell for these equations that you're doing it correctly if you get something in the end that's a true statement. We know that 3 to the 4th is 81, so we're good on that one. You're welcome to do the second one on your own, or you can just watch me do it. So we're going to write that as 5 is the base, so we write it as 5 to the power of -1, the answer to the logarithm is our power, is going to be equal to 1/5. So the next two, we're just doing the exact same thing that we just did, except in the opposite order. For number 3, we have 5 to the x power equals 83. As a logarithmic function, we are going to write log base 5 of 83 is equal to x. So keep in mind that the answer to the logarithm function is the exponent. The base of the logarithm is the same as the base of the exponent. For number 4, we get log base a of 87 is equal to 1/2. My next examples are evaluating the logarithms. You might be able to guess one way to do it. There's a few ways to do these. So for number 5, we have log base 3 of 27. We're evaluating that. Basically, what we're doing is we're trying to figure out what exponent, if you do 3 to which exponent, that gives us 27. So I usually look at these and I say 3 to which power is 27. So that's usually how I do that. Other way to do it, and some people prefer this way, I don't really care which way you choose, is you can write it as log base 3 of 27 equals x, and you can actually rewrite this as an exponential function like we did for numbers 1 and 2. When you do that, we get 3 to the x equals 27. We know that to get the power, if we do 3 to the 3rd, we get 27, so my x value is 3. Either way works for me. These ones you're just going to be evaluating and getting a numerical answer. You don't really need to show a lot of work, but if you want to do it using writing as an exponential function, that's certainly okay. For number 6, we are trying to figure out, 2 to which power is going to give us 1 over 16. There's really 2 ways that you can do this depending on how good you are at seeing things with fractions. I think for many people, one of the easiest ways to do this type of problem is to rewrite this equation so that they have the same base. So I have 2 to the x on the left. On the right-hand side, I have 1 over 16. So I know that 2 to the 4th gives me 16. In order to get that as a fraction 1 over that, it would have to be to the negative 4. So my answer for that one would actually be x equals negative 4. Be careful that you don't do negative 1/4, by the way. That's a very common mistake that people make on here. Negative 1/4 is something different. We'll talk about that later on. But any way that you want to do this, if you can see in your head that 2 to the negative 4th power gives you 1 over 16, that's great. Keep in mind that if you have an answer that is a fraction, your exponent needs to be a negative. I'd like to do a few graphs, and I actually would like to show you how the graph of y equals 2 to the x power and y equals log base 2 of x are related. I do also want to point out that y equals 2 to the x and and y equals log base 2 of x are inverses. So you might be able to guess that their graphs are actually going to reflect over y equals x. But let's go ahead and actually draw them first before we do anything else. So we're going to start with y equals 2 to the x. I'll do that one in yellow. Usually I like to do a table when I draw those. If you know what it looks like, that's even better. I think with exponents, people aren't as comfortable with those, so if you don't remember what it looks like, that's fine. So I have these values right here. I'm actually going to do x equals 3 also. So now I can go ahead and draw my graph. And I'm hoping that you remember this from the last section. I do want you to notice that the range of this is that y is going to be greater than 0. The domain is all real numbers. And we do have a horizontal asymptote at y equals 0. So those are the 3 important things I want you to notice about this exponential function. So this is y equals 2 to the x. Let's go ahead and do the logarithm also. So with my logarithm, I'll use green for that one. For my x values, I'm actually going to choose x values that I know are going to give me nice values. So let's think about some negatives. So let's say we had like -2 or something. If we were trying to find our y, we would do log base 2 of -2. We would be saying 2 to which power, you can even think of it like this. I'm going to write it as 2 to the y. We can think about 2 to which power is going to give us -2. Actually, there is no such power that exists. You will not find anything that gives you a negative number. Same thing happens with -1 and any other negatives. So those are non-existent. Let's try 0. So we're going to do the same thing. We get log base 2 of 0. We're thinking 2 to which power gives us 0. And the answer is not 0. I'm going to tell you that right now. Actually, there's no value that gives us a 0 either. So when we do that, this should have been a y, by the way, not an x. When we do that, you will find that -2, -1, 0 are all not in the domain. And actually, no negative numbers are in the domain. So let's try some positives. Let's try 1, 2, we can try 3. So for 1, we have log base 2 of 1. We're thinking 2 to which power is going to give us 1. And actually there is a power, and that's going to be 0. We can do the same thing for log base 2 of 2. If you think about 2 to which power gives us 2, it's going to be 1. If you do log base 2 of 3. You're thinking 2 to what power gives me 3? That one's pretty hard to get. There is an answer to this. It's really hard to get without your calculator, so we're not actually going to worry about that one right now. We will try if we have log base 2 of 4. If you think about 2 to which power gives you 4, it is going to be 2. The next one that will give you a nice answer is if you go all the way down to 8. Sorry, I'm running out of room here. You'll find that log base 2 of 8 is 3. That's another nice one that we can use. So let's go ahead and draw these points that we have. So we have these values right here. I'm going to actually say to be careful about this next part, because just because we don't have any values between 0 and 1 listed on the graph doesn't mean that they don't exist. So we will actually have some values right here. We can kind of tell that that's the way it's going to be because we know that this graph needs to be a reflection of that yellow one over the line y equals x, because we've already established that those are inverses. So just make sure that you don't lose that part of it. You need to have your full graph to get full credit on this type of thing. So now let's look at our logarithm domain and range. So first of all, we have a domain. Domain is not going to be all real numbers. The domain is all values such that x is greater than 0. The range, however, is going to be all real numbers. The other thing that we have is we have a vertical asymptote at x equals 0. So the one thing I really want you to notice on this is that my horizontal asymptote of the 2 to the x is going to correspond with the vertical asymptote. The range of 2 to the x corresponds with the domain of the logarithmic function, and the domain of 2 to the x corresponds with the range of log base 2 of x. So that's all the properties of inverses are satisfied. So you can kind of just use those to help you out when you're thinking about how to graph these. Just remember that we do actually have asymptotes for both of these graphs, so you don't want to cross over either the x-axis for the exponential, and you don't want to cross over the y-axis for the logarithmic. And the other thing, though, is that the range of the log is all real numbers. That means it's going to go up forever and ever and ever. It goes up slowly, but it does go up forever and ever. I'd like to just talk about two important logarithms. So the first one's called the natural logarithm, and we write that as y equals ln of x. So the natural logarithm is going to be a logarithm with base e. The other one's called the common logarithm, and the common logarithm is actually just written as a log with no base. That's actually equivalent to log with a base of 10.